Hmm. So you can just type in some message, hello. Hello all. Uh, if you can hear my voice, please send a chat message. Okay, great. Uh, so, welcome to this online broadcast for the AI Constraint Satisfaction course. As you know, this is an 8-week course, and we are entering the 6th week now, essentially. What I will do is I will do a quick recap of everything. I will try to highlight what CSP or Constraint Satisfaction is all about. And we look at some examples. Some of them you may have seen earlier, some of them may have come in your quizzes, some of them will come in the quiz in this week or the next week, and we'll try and understand that. So I have made a set of slides for this, which I will shift to now, and I will use the slides. And once the slides are over, we can come back for a face-to-face discussion again. Okay, so we have just started this slideshow, and it will appear on your screen in a minute, and I'll wait for that because I have a parallel screen running here. Okay, so essentially what we have been trying to say is that constraint satisfaction problems are a way of uniformly capturing all different kinds of problems that you can want to solve in AI, and you pose the problem as a CSP, and then you can use an off-the-shelf technique to solve it. What we are doing in this course is to learn how to solve CSPs, and throughout today's lecture, we will try to use simple examples, mostly map coloring examples, and look at the different ways that you can solve the CSP essentially. Okay, so here we go. So if you remember the definition of a CSP, the first thing you need is a set of variables. In this example that we have 7 variables which we have called A, B, C, D, E, F, G. Each variable has a domain of values. So if you can somehow map the variables on the left to the domains on the right, you can see that A has domain R and B, which we will understand to stand for red and blue, and mostly we will be talking about map coloring problems. Domain E, which is on the top, has the variable E has domain green, red, and white, and so on. So each of the variables has their domain. So this is one thing about CSP, is that every variable has their own domain. In this particular example, the map coloring example, all the values of all the variables are colors, but that is not necessary. You can have, for example, one variable can have an alphanumeric value, another variable can have a numeric value, and all kinds of things are possible essentially. Then the main task is to assign values to each variable from their domains. And typically, we would choose a fixed ordering, which in this example, and this is a slide which you might have seen, or we will put it up tonight essentially. So we have chosen an order. As you can see, we will process G first, which means we will try to look for a value for G, and this is indicated by the number 1 written next to the domain of G in red color. After that, we will move to D, then to B, then to F, then to E, and then to A and C. So the task is to try and find values for these variables from their respective domains. Actually. So as I said, we will be talking mostly about the map coloring problems, and this is another example of the map coloring problem, which is I think going to show up in an assignment that you will have to do next week, I think, which is on look back methods, back jumping, and so on. So in this domain, we have shown the variables. There are 6 variables: A, B, C, D, E, F. The constraint graph on the left captures the binary constraints between different regions. So on the right, you can see 4 different solutions for the map coloring problem. But you can also see that A is adjacent to E, C, and D, and that is shown by having edges from A to E and to C and to D, essentially. So the constraint graph tells you which nodes are adjacent to other nodes, and the constraint is that the color that they get or the value that they get must be not equal. And the domains for each of the variables are given below. So A has domain B and G. So B is blue and G is green. B has domain blue and red, and so on and so forth. So we will look at how such problems are solved. Okay, so as I said, the task is to assign a value to each domain, each variable from its domain, subject to a set of constraints. In the map coloring problem, the constraints are that 2 regions which are next to each other must not have the same color. And that is represented by the constraints on the right hand side that you see, which is a not equal to constraint, which basically means that the value of E should not be equal to the value of G, for example, or the value of E should not be equal to the value of B, and so on and so forth. So every edge shows which 2 regions are touching each other, and the constraint that we are using is a not equal to constraint. But in general, of course, constraints can be anything, and we have represented constraints as sets of tuples in the examples that we see. But today, let's stick to map coloring so that we can again clarify on the techniques that we use for solving CSPs, essentially. So another diagram that we often use is the matching diagram. The matching diagram, as you can see, that for the 7 variables, the matching diagram is on the right. It also has the order in which you are going to process them. G is going to be first, D is going to be second. All that is shown in the red color. And the values for each, the matching diagram contains the values that the variable can have. And an edge between the value in one domain, for example, an edge from G to F that you can see, there are 4 edges going from G to F. And the way to understand the edges is that if you choose a value W for G, for example, you can choose a value R from F, because W and R are different colors, but you cannot choose a value for W in F, because then they would be the same color. Likewise, if you choose a value R from G, you can only choose a value W from domain F. But if you were to choose the value blue for G, then you could choose any of those 2 values for the variable F. Okay, so this is a now posing of the problem. We have a map coloring problem. We have the domains and the matching diagram and the order in which we are going to process the variables here. And now let's see how can we solve such CSP. So again, I would like to emphasize the fact that even though we are looking at map coloring, the techniques that we are studying are general in nature, and any constraints can be expressed using the explicit notation that we have been talking about. Okay. So how do we solve CSP? So essentially there are 2 approaches. One is search, which is basically trial and error. You try different combinations of values for the variables till an assignment that satisfies all the constraints is found. So we'll start with search, but we will see that search is one way of doing this. The other way is propagation, which is like doing reasoning. And the idea of propagation is to exploit the information contained in the local constraints to prune the search space so that the search algorithm has to do less work, essentially. So very often we can of course solve the entire process by propagation, by reasoning, but that would involve an enormous amount of work, essentially. We can also solve the problem entirely by search, but that also would involve looking at all the possible combinations. So very often we prefer a trade-off between search and propagation. We do certain amount of propagation and then we do search, essentially. So propagation is meant to reduce the search space for search, and search is supposed to find the solution for us. So what are the kind of improvements we can do on search? The first improvement we can do is that we can do look ahead, and this is something that we have already discussed in some classes, and we will illustrate it again today. Uh, the idea of look ahead is that before trying a value for a variable, look at the future variables to check if they will have consistent values. And based on that, you decide whether you want to choose a value for a variable. The other thing that we can do is look back, which is what we are just about to begin. Is that if you have got stuck at a dead end, then instead of just going back to the last variable as depth first search does, or as the algorithm backtracking does, we will try to identify as to which is the culprit variable which is causing the inconsistency, or which is causing the dead end, and jump back to the culprit to try a new value instead of blindly going back to the last variable. Other things we can do is dynamic ordering of variables. Which variable should you assign values to first? So in the examples that we are looking at, we will assume that variables will be chosen in a fixed order, which is pre-decided. And we have also looked at certain techniques like min width ordering and min induced width ordering, which are supposed to be good orderings for solving CSP. So we'll assume that one of those techniques has been applied, and then we are processing the CSP in a fixed ordering decided by the algorithm, which like some min fill or something like that. And the last thing that we can do, and this is true especially for large problems, is no good learning, is that if you can remember what combinations of partial solutions fail or partial instantiations fail, and if you encounter the same combination again, then you don't have to proceed further from there, and you can backtrack immediately. So you can see that all these these things are designed to improve the search algorithm, which is basically backtracking, but maybe combined with look ahead, or combined with look back, or maybe combined with no good learning and things like that. Or even dynamic ordering of variables, that you may decide dynamically as to which is the next variable that you will process, and we have looked at some of those algorithms. Okay, so the first thing you do is that you generate a search tree. So what you see on the right hand side in the small is that original constraint graph that we had with the 7 variables. Then on the left hand side, you can see the order in which we decided to process the variable: G first, then D, then B, then F, then E, then A, and then C. So essentially, the search algorithm implicitly constructs a search tree like this, and searches this tree in the depth first fashion essentially. So it first tries of the 3 values for G, which are W, R, and B, it tries W first. Then it tries the value of G, green for D, then blue for B, and so on and so forth. And essentially, it tries to assign values which are consistent to this thing. So essentially, backtracking does depth first search on such a tree, and you can see that somewhere on the right hand side there is a solution which is shown here, which shows that D should get red, D should get green, B should get green, and so on and so forth. So the path in the red is the solution, and that is when the algorithm will terminate. Okay. So one thing that we have already studied, and which we will quickly recap before we look at the look back methods, is forward checking. So what does forward checking do? So this diagram, I hope you will remember that these are if there are 10 variables that you are trying to solve the CSP for, and if you have already assigned a value for 5 variables, and the values that you have chosen are shown by this shaded diagram here, and now you are considering a value for the 6th variable, which is x6, and let us say you are considering the value which is shown in blue color for this 6th variable. Now in this whole set of values that you can see, there are certain values which are shown in dashed squares, and these are values which have been deleted by forward checking up to now. And you can see some values below in x8, x9, which are shaded gray, and these are values which would be inconsistent with the blue value that we are about to choose for x6, and therefore forward checking would remove these values even before we go to those variables x8 and x9. So that's the basic idea of look ahead, is that look ahead to see if other variables will have values for solving those problems.
Is it whether the search tree is similar to that of alpha?
So there's a question whether the search tree is similar to alpha beta, and the answer is no, because alpha beta algorithm is used for game playing, and if you have done an AI course, you would have encountered that there. And game playing is between 2 players, so it's a 2-player a problem. So it's an adversarial situation. So you have typically two players, which we call max and min, and the alpha beta algorithm is designed to play a game between two players. Whereas all problems like CSP, these are, you can say they are one player games, in the sense that there is only one player who is deciding the moves, and what the moves that the player is trying to decide is that which values to give to each of the variables. And once you can uh, assign values which are consistent with all the constraints, then you have solved the problem. So it's like solving a puzzle in some sense, but it's done only by one player. Okay. So we saw this example in one of the lectures. So supposing you have to place these six queens. So this is an instance of an n queen problem where n is equal to 6. So you have six queens, and we will label the queens as 1, 2, 3, 4, 5, 6. And then we want to place them on the chessboard so that no queens attack another queen. And what we want to illustrate here is this forward checking or look ahead method. So for example, if you place the first queen in column A, then the squares that the crosses that you see on the different squares of the chessboard say that nothing else can be placed there. Why is that? Because this queen number 1, which we have placed in column A, attacks the entire column A. It attacks the entire diagonal that you see on the right hand side, and it also attacks the entire row, which means basically that you cannot put a queen in any of these things. So then the second queen that we want to place, and assuming that the order is 1, 2, 3, 4, 5, 6, can only be placed in column C essentially. And because we can't place it in column A or column B, so when we place the second queen in column C, and again we look ahead to remove some squares where queens cannot be placed. So if you look at, for example, row number 4 or queen number 4, there are already 4 crosses put on that, which means that a queen cannot be placed in any of those 4 crosses, because if it is placed on the first column A, it will be attacked by queen 1. If it's placed on the C column, the third column C, it will be attacked by queen 2. If it's placed in column D, it will be attacked by queen 1 again. And if it's placed in column E, it will be attacked by queen 2. So you can see that already a lot of the chessboard has been eliminated as to where you should try the future solutions. And this is one of the things we are trying to do by look ahead, is to reduce the search space so that the algorithm doesn't have to search the entire set of combinations, but only what look like possible. So for example, for queen number 3, we will not even try A, B, C, D, but only we will try E and F. And first we will try E, assuming that we do it in this order. So once we place queen 3, we see that more crosses have been put on the chessboard, but still every row still has some blank squares, which means we still have places for queen 4, 5, and 6 to be placed. But the moment we place queen number 4, you can see that the row for queen 6 has become totally crossed out. There is no place that you could place queen 6, because it would be attached by either queen 1 or queen 2 or queen 3 or queen 4. And so there's no point even trying out placing a queen on queen 5. So the forward checking algorithm backtracks from this point itself. So let's illustrate the same algorithm with the map coloring problem. The idea is still the same, that you keep trying values for variables in a particular chosen order, and you keep doing this look ahead. And if at some point some domain of some future variable becomes empty, then you backtrack. So in this example that we are looking at right now, we have tried 4 queens, queen 1, queen 2, queen 3, queen 4. But the domain of queen 6 has become empty because everything has been crossed out. So we backtrack from that point itself and try a different value for queen 4. Then we try a different value for queen 3, and then so on. So depending on how much you want to backtrack. So let's go back to the map of coloring problem that we had seen. And we have already talked about the constraint graph, which is on the left, and the matching diagram, which is on the right. And the order of variables has been already decided. G is going to be first, B is going to be second, C is going to be B is going to be the third, F is going to be the fourth, E is going to be fifth, A is going to be sixth, and C is going to be the last variable that we will try a value for. So essentially now we are doing search, and you can see that by looking at the matching diagram, we can understand what search is trying to do. Is essentially we are trying to, in some sense, move from one variable to the next variable through the edges that we have. We can only move to another variable from an edge which connects the two variables, because an edge represents the set of allowable combinations. So as we discussed earlier, with queen with region G, if you choose W, then you can only choose R. You can't choose W from there. So the constraints have to be respected, and we will do a certain amount of look ahead essentially. So we will look at forward checking the same algorithm we saw with the chessboard and see that what happens. So initially you try, because we are going to look at variable G, we try the first value which is available to us, which is W, and as a consequence of it, we see that from W you could not have gone to W in F or W in E, because they are touching countries. If you color G white, then you cannot color E white and you cannot color F white. So forward checking will remove those values from these two domains of E and F. It doesn't matter in which order you are going to process them. These are both future variables, and the values that you are seeing in red are inconsistent with the choice W for G, and therefore they are removed from this. So this search algorithm proceeds in this manner. This is a presentation I have done in class, and we are kind of doing a recap. So I'll hurry through this so that we can look at something which is we have not done in class. Essentially. Okay, so the second variable we want to try is D. We have already got a value W for G, white for G, and now we are saying that the first value which is available to us, which is green for E, we choose, and as a result of which we end up deleting certain values which are inconsistent with green. So wherever there was a touching country, so you can see that on the left hand side that the variable D was connected to variable C essentially. So you could not choose a value green there essentially. And if you choose a value, uh, so we basically remove the value green from there. Then we try a variable for value for the variable or region B, and we choose the first available value, which is B. And as a result of which, we find that this domain of C has become empty. We had started with two values in the domain of C. We removed B because it was not consistent with this value for variable 3, and then we removed C because it was not consistent with the value R. Sorry, we removed the value Z from C because it is not consistent with Z in F, and you can see on the left hand side that C and F are touching countries. So by the time we try the value of B for country B, a blue for country B, we have ended up, or by the time we try value R for country F, we have ended up making the domain of C empty. So the algorithm backtracks from variable 4 and goes back to a different value for variable 3. So the second variable for 3, that is green, which is available, we choose that. Then we choose a value for red for variable F. Then we go to the fifth variable, which is E, and we choose a value red for that, which is consistent with what you have seen so far. Then we go to the sixth variable, we choose a value B for that, and again we find that the domain of C has become empty. So we backtrack from there, and we now have to go back to the all the way back to the first variable G and try a different value for that. No, we tried a different value for another variable. Anyway, we have to. You can sort that out. Okay, so the next algorithm that we want to look at is another variation of look at. This is called full arc consistency. What full arc consistency does is that for every value that it chooses, it does full arc consistency amongst the future variables. And essentially what happens is that it rules the domains much faster. So for example, here we choose, again, we start with the first value white for region G, and when we do full R consistency for this, we can see that from many domains, many values have vanished. And then all this is happening simply by the choice of white for G. This propagation is happening amongst different variables. And even at the moment we have just decided upon the first variable, which is G, and the value white, we have found that the domain of E would have become empty. So we backtrack from the very first choice itself. So this white was the first choice for G, but full R consistency look ahead showed us that that is not going to work, because in the future this domain E will not be able to get a value. And between forward checking and full AC was a third algorithm which I will move to, which is called full look ahead. And we have done this, so I'm just trying to hurry through this. Uh, in full look ahead, you do only one pass over the future variables. You don't do complete R consistency, and but you do look you do this revise operation. If you remember, for doing R consistency, you do it once for every future variable essentially, or once for every pair of future variables in both directions. If you do it only in one direction, then it is partial look ahead. So if you choose W or white for G, and now you're doing full look ahead, then at the you end up removing B from A, B, and D, because they are not consistent with the value for C, and you end up removing some more variables because you are doing this full look ahead. And again, you discover that the domain of E has become empty. So this white for J is not going to work. So even full look ahead could do that, which is doing less work than full AC, but it's doing more work than forward checking. Forward checking had to try out a lot before it backtracked. Full look ahead and full AC just tried the first value and said it's not going to work. So that's the power of reasoning being added to search, that when you're considering the value white for G, by doing this look ahead, by doing this constraint propagation, by doing this consistency propagation in the future variables, you can see that this value for white is not going to work essentially. So you can see that it's going to do less amount of work searching, but it has to do this extra work doing propagation. So it's always a trade-off between searching and propagation. So this is showing this second value for the first. So since it decided that white cannot be used for region G, it's trying the red value, and it tries a few things, and it does a little bit of propagation, and it's got values for the second variable D, which is green, the third variable B, which is also green, and still the domains are fine. And after this, it's able to find the solution. So what you see in the shaded values are the values in the solution for this map coloring problem, and the blue edges that you see tell you that which are the consistent values that you have chosen. So for example, for region E you have chosen white, and region A you have chosen red, and that connection is consistent, is shown by the fact that there is a blue edge between them. Okay, so this is how the matching diagram looks when the full look ahead algorithm terminates. Okay, so let's move on to other things now. One thing that we said is that by choosing a proper order of variables, you may cut down on the search space. One approach that we have seen is this min width ordering or min induced width ordering. That looks only at the topology of the constraint graph. It doesn't look at the set of values that variables have. Now, if you look at these three variables, A, B, and C, and you can see that on the left-hand side, that A has three values. This is just some simple example that we are constructing. A has three possible values, white, red, and blue, but B has only one value, which is green, and C has only one value, which is B. If you try A first, then you will generate a search tree which has got all these 9 nodes. Whereas if you were to try B and C first, which have only one variable, then you will generate a smaller search tree. And you can see that the heuristic that we are using here is that choose a variable which has the smallest number of values in its domain as the next variable to process. And this is what we do when we do dynamic variable ordering in CSPs. Okay, so now let's get back to more of this constraint propagation. This thing we just did look ahead. So let's get back to propagation. Then we will look at directional consistency, and this is what we have been studying in the last few classes, last few weeks. And so let's look at that again. So again, we have a slightly simpler map calling problem, and you might recognize this, that this was given to you in the second assignment or second week assessment, and you were asked to show uh, what are the values in the domains after our consistency has been done. So let's just quickly go over these examples which came in weeks 2, 3, and 4, and look at the solutions for them. Okay, so what is on the left hand side? You see the constraint graph, and you can see that the five variables have the allowable colors given to them. On the right hand side, you can see the matching diagram for the same constraint matching constraint satisfaction problem. Okay, and we want to illustrate our consistency. So, assuming that somehow we have chosen this order that we are talking about, uh, first we remove these values b and red from the domain of d. And why are we doing that? We will remove the value of b from the domain of d whenever we do a call of revise d with respect to variable c. And you will see that if you choose blue for d, then you can't choose the value for c, because c has only one allowable value, which is blue essentially. So we remove the value of blue from the domain of d. In a similar fashion, we will remove the value red from the domain of d, because D is adjacent to E, and E can only be colored red in this very small example that we have concocted. And if we choose red for D, then we can't choose a value for E. So what our consistency does, or one of the loops in that does, is to remove this from the domain of D. Next, we remove two values from the domain of B, which is the values blue and green. Why do we remove blue? We remove blue from B because B is adjacent to C, and C can only get blue essentially. Likewise, we remove G from B because by now D has only green left. So if we color the region B as green, then we can't give a color to G, and so we end up removing that. So actually, this is a very small network, and you can see that by somehow very magically choosing these revise operations, we have reduced the graph to this. And the algorithm AC1 will do this with brute force. The algorithm AC3 that we looked at will do it in some slightly more intelligent way by propagating which variables to revise with respect to which other variables by seeing what has changed and so on. But by the end of the process, whether you do AC1 or AC3, this is what the graph will look like, and this is the answers that you were expected to give. That the domain of A has blue and green, the domain of B has red, the domain of C has blue, the domain of D has green, and the domain of E has red. The next thing we talked about was path consistency. So path consistency or tree consistency basically says that for every two values that you can assign to two variables, you must be able to assign a value to the third variable. And if you cannot do that, then that particular combination of values from the two variables must be removed essentially. So if you are doing path consistency on this particular problem, you can see that as a first step, if you were to revise B and D, which are shown in blue here, with respect to the variable C, then the four edges that you see, which are shown in red dash, these will end up being removed. And why will they be end up being removed? Because if you choose a value for B for blue for the variable B, then you cannot choose a value for B for C. So B with anything, if you choose blue for B and green for D, or if you choose blue for B and red for D, it doesn't matter. You will not be able to choose a value for variable C. And we had observed that what we are doing in path consistency is checking for triangles, that between any three variables that we can see in the matching diagram, we should be able to see triangles. So if you connect blue to green, blue in B and to green in D, you cannot make a triangle with variable C, because you cannot choose the value B because in blue in C, because it will conflict with the blue in D. So as a result, all these four edges are removed from the relation RBD. So whenever you're doing path consistency, you are pruning relations essentially. So all these four edges, each edge, remember, is part of a relation. The relation RB originally said that if you choose R, you can choose green and blue in D. If you choose blue, you can choose green and R and so on. But now you find that in either of the two variables, any edge which has blue on either side has to be removed, and the algorithm and the graph looks like this. Now, supposing we revise B and D, which is the same set of variables, with C, so that we have just done. Okay. Next, if we revise the set AB, the relation AB with respect to the relation D, you must remember that even though there is no edge between variable A and D, if there is no edge in the constraint graph, it means it's a universal relation, and it means that any combination can be allowed. But nevertheless, with all those combinations being allowed, we still cannot complete a triangle by choosing blue for B and green for A, because this blue doesn't have an edge going into D, and that edge was removed in the previous call to revise, and it said that you cannot, if you choose blue here, you cannot choose anything else. So you end up removing this red edge from the relation AB, and now the now the graph looks like this. Next, if we revise AD, this edge AD, which is a universal edge with respect to B, then you can see that with all these three edges, which are BB, B and B, which is allowed because they are not touching each other. You can choose B for A, you can choose B for D, and nobody is stopping you from doing that. But if you do that, you will not be able to choose a corresponding value from the domain of B. So we'll have to remove these red edges that we see at the bottom, which is blue connected to blue, green connected to blue, and green connected to red. And one of the reasons for that is that anything with blue in B and D, we know that they are not working properly. Essentially, if we had done strong path consistency, we would have actually removed the values B and B from the domains of B and D. And we will see this a little bit later when we talk about strong consistency, but we will look at it in a directional consistency example. So if you remove these three edges from the universal relation, so this universal relation would have had 6 edges, right? Because there are 2 variables on the left and 3 variables on the right. Of those 6 edges, we remove these red edges, and what we are left with are those 3 other edges, which says that okay, you can choose this combination. If you can choose B with A, you can choose blue for A, and you can choose green for D. So in effect, what we have done is we have induced a new relation, and the new relation is the relation RAD, which is showing now on the constraint graph on the left, which says that AD also has a new relation. But this relation, mind you, is not the original relation, which was not equal to because of map coloring. This relation says that if you choose B for A, you can choose green for D, or if you choose B for A, you can choose red for D, or if you can choose green for A, you can choose green for D. That's allowed. So this is a new induced relation. After this, if we do E and D with respect to A, we will end up removing this edge RB that you can see between E and D. And the reason for that is that we cannot complete a triangle with them. Even though the relation A and E is a universal relation, we cannot complete a triangle because from B, we don't have a connection to any value in A. From this color blue in D, we don't have a connection to any value in A, and therefore we'll end up removing this edge. So again, I will say that if we had done strong path consistency, we would have removed these blue values and saved us the trouble of doing all this reasoning for path consistency. And that's an advantage of doing strong path consistency. And finally, if we do the edge B and E with respect to D, originally it was a universal relation, which meant it had 3 edges because there's 1 value in E and 3 values in B, and you say that any combination is allowed. But again, because we can't complete triangles with D, we end up removing 2 edges and we are left with only 1 edge. And at this point, the network is entirely path consistent, and you should be able to verify that if you take any edge between any 2 variables, you take any other variable, you will be able to make a triangle with that edge, with the 3rd variable. So now let's move on to the notion of directional consistency. Why did we move to directional consistency? because our consistency or path consistency or in fact any level of high consistency involves a lot of work. And if we have already chosen an order of processing of variables, then we had shown that directional consistency is enough. So for this small, uh, again map coloring problem, you can see that if A is connected to B and B is connected to C and to D, C is connected to D and so on. And if we decide that we'll process the variables in the order A, B, C, D, E, then we only need to do a limited amount of consistency enforcement. And if you remember the algorithm, the way we do it is that we first make uh, uh, we go down from the last variable to the first one. The last variable is E, then the second last is D, then the third last is C, and we keep making whatever edges we have connected to them consistent. So in this example, E is connected to D. So first, what we do is we revise this variable D with respect to the variable E. So we call revise only in one direction, and this removes the value read from the domain of D. And by looking at this matching diagram, you can see that the reason for that is that if for some reason we had chosen red for D, we would have been able to choose red for E, which is the adjacent region. So this directional arc consistency is saying that you remove this value red from the domain of D. So that is the call that we have made, revise D with respect to E. Then we move to the second last variable, which is D. D is connected to C and to B. So we will have to revise D, uh, both C and D with respect to D. But you can see that there are no problems here. If you choose B for the variable C, you can choose green for D. So that's fine. If you choose green for B, you can choose blue for red. If you choose blue for B, you can choose green for D. And if you choose red for blue, you can choose any other color from D essentially. So it has no change here. Next, when we do B with respect to C, when we revise B with respect to C, we see that if we choose blue for B, we will not be able to choose a value for C. So we remove this value blue from the domain of B essentially. And finally, when we do A with B, we don't have anything proven from this. Okay, so we had also discussed at various times as to how much is the degree of consistency one must enforce for search to become backtrack free. Okay, so what have we done in this example? In this example, we have said that we are doing directional arc consistency, which means we first made uh, uh, all variables consistent with respect to E, then with respect to D, then with respect to C, and then D. And we have got a network which is directionally arc consistent, but it is not backtrack free. Why is it not backtrack free? And that is shown here. That if you were to choose uh, in backtrack free search, you can choose any allowable value from the next variable. If you were to choose B from the domain of A, then you are allowed to choose either green or red from B. So let's say we choose green, which is shown in light blue color here. Uh, then you can choose blue for C essentially. So having made this set of choices, blue for A, green for B, and blue for C, you can see that choose blue for D because C and D are connected to each other; they are adjacent, and C already has a blue color. Likewise, B and D are also connected to each other, as you can see in the constraint graph. If you were to choose a value, because we have chosen green for blue, we cannot choose green for D. Okay, so the green for blue prohibits us from choosing green for D. The blue for C likewise prohibits us from choosing blue for uh, D, and we'll have to backtrack essentially. Essentially, we will have to go back and try a different value for blue for region B or a different value for region G. So this illustrates the fact that our consistency is not enough to do backtrack research, and because the width of this graph is 2 and the induced width is also 2, you need to do at least path consistency. So let's again look at an example of, I think this was not given in the quiz, but it's another example that we can look at. Supposing we have chosen a min width ordering. Remember that the min width ordering says that the variables with least number of connections should come towards the end essentially. So we have pushed A and E towards the end, and the variables b, t, c, which form a triangle we have put in the beginning, and the corresponding constraint diagram would be the matching diagram would look like this. So again, we do directional path consistency. So first we will do for variable e, and you can see that variable e is connected to variable d, and we will see that the value of r in d, because they are touching with e, is not consistent with the value of e. So we'll remove the value of r from the domain of d. After that, we do uh, directional r consistency with respect to a, then we do with respect to b, and then we do with respect to c, with respect to d, and all of them don't introduce any change in the variable. But now we are claiming that the search is become backtrack free. Why is it become backtrack free? If you see this diagram, the only choice you have for variable c is blue, and that means you will end up choosing green for d because there is an edge between them, and you will end up choosing red for blue. You cannot choose blue for b, and the reason for that is because b is also adjacent to c, as you can see in the constraint diagram on the top. You cannot choose that value for D. So, and you obviously cannot choose green because it is adjacent to D. So, even though they are there in the domains, and the domains have not been entirely pruned, the network is not fully R consistent. It is only directionally R consistent. But in this particular choice of order, uh, you chose blue for C, you chose green for D. You were forced to choose red for blue for the reason we just discussed, that we cannot choose green because it will conflict with region D. You cannot choose blue because it will conflict with region C essentially. So now you're forced to choose R for blue, and you can choose any one of them, and that will work in the solution. And in the end, you'll end up choosing red for this. So you can see that directional R consistency with min width helped in this particular example, but that's not something that we can claim all the time. So let's now talk about directional path consistency. So again, let's assume that the order of processing of the variables is A, B, C, D, E, and again we will move from the last variable to the first one. First, we will try to make every pair of variables consistent with E, then every preceding pair of variables with respect to D, then A, B with respect to C, and G, A with respect to B. Now remember that when you do directional path consistency, if you go back to the algorithm, you will see that you not only do revise 3, which is revising an edge with respect to a variable, but you also do revise, which is essentially R consistency. So you're doing both at the same time. So in this example, uh, we do the following. Uh, we first do, we are doing everything with respect to variable E. So when we revise CD with respect to E, we end up removing this edge BR, which I've shown in red, going from region C to region D. If you revise BD with respect to E, then you end up removing two edges. One is B to R, and the other is G to R, because they cannot be extended to E. That's basically because if you choose red for D, then you can't choose the value for E. And again, if you revise AD, now remember AD was a universal relation to start with, because we had no constraint. A and D were not regions which were adjacent to each other. But nevertheless, we end up removing these edges which are shown here, BR and GR, from this. And the reason for that is again clear, is that they involve the value R for domain D, and that will not be allowed. But once we remove this, we end up inducing a new relation between A and D, which is shown in the constraint graph in blue, and the new edges are shown also in blue in the matching diagram below. But remember that when we do uh, these revise 3, we'll also have to do revise itself. Okay, so let's also first finish the revise 3 part. So we do BC with respect to E, no change. AC with respect to E, no change. AB with respect to E, no change. So we are done with all the pairs of variables, at all pairs of 4 variables, ABCD with respect to E we have done. And then we do the revise with respect to E. So when we revise D with respect to E, this value R goes off from this. And when we revise C, B, and A respectively, nothing goes. So we are left with only one less value in this, and this is how it looks. Next, we do this directional path consistency with respect to variable d, and you can see that when we revise BC with d, we end up removing the GB edge from BC, and the reason for that is that when you choose G from B, you cannot choose G from D, and if you were to choose B from C, you cannot choose D from D. So you can't form a triangle with the variable D. So this red edge has to be removed. When you do AB with respect to D, nothing happens, and this is how the graph looks. Then when you revise the domains, make them arc consistent, no change happens. And then you finally revise the edge AB with respect to C, and we end up removing these two edges, BG and GB. And you can see that the reason for that is that they have values B and G in D. They will conflict with that. You will not be able to make a triangle with that. And therefore, because if you choose B and G here, you can't choose either B or G in this one here. So those two edges will go. And then when you do the revise with respect to C and B, then these values G and B will go away from the domain of B. And in the end, we will be left with this matching diagram. What we have done is directional path consistency, which is actually strong directional path consistency, because we have removed values from domains and we have removed edges from relations. And we are claiming that the search is backtrack free, and we can see that you choose whether you choose B or G, you will end up choosing red, which is fine, and blue with for C, which is fine, and you will be forced to choose G for D, because you can't choose blue because it will conflict with the value blue that you have chosen for A. But you can choose green and you can choose red. So as you see, remember that when you do the assignment, when you assign a value to B, it must be consistent with its predecessor, which is A. When you assign a value for C, it must be consistent with B, because B is a relation there. When you assign a value for D, it must be consistent with respect to both B, C, D, because there are edges in the constraint graph, and that's why we can't choose a value for D. Even though it's there in the domain, and this is only directional consistency, we have not ruined everything, but the search has become backtrack. So as a last example, we will look at directional path consistency with the other ordering that we had seen, which is the min width ordering, which is C, D, B, A, E. And remember that we got this ordering because these variables were the ones which are least connected were processed last, essentially. So first, when we revise everything with respect to E, when we revise B and A, nothing happens. When we revise D and A, two edges get removed from there, and both the edges involve the value R in D. So if you choose R in D, then you can choose the value for R in E, and you can see that there is an edge in the original graph from between D and E. So you can't choose this value R. So this relation itself is ruined further. But C and A doesn't mean any change. So this is this thing. When we do D and A, we remove these two edges. A minute. D and A, we remove those two edges from the universal relation, and therefore we induce a new relation, which is, you can see, is between variables B and A. And this new relation is shown with blue lines here, essentially. Then finally, when we do variables DB, CB, and CD with respect to A, we see these red edges are removed from these relations, and we are left with a graph like this. And when we do our consistency, the value D, which is in the value read in domain D, which is conflicting with the value read in domain E, is removed from there. And then we do a few more revise 3 and revise B operations, and we are left with a graph which we claim is backtrack free. So again, why is this graph backtrack free? You can see that if you choose the value blue for region C, you can only choose value green for region D, because that's the only edge that is there. If you choose blue for C and green for D, you can only choose red for B. You cannot choose blue even though there is a path from G to B here, because this blue would conflict with the value for C, and there is a relation between B and C. So you can only choose Z for B, and we can choose either of B or G from region A, and finally we will get the value Z for region E. Okay, so this is what I wanted to say, uh, and I will stop sharing uh, the slides now, unless somebody has a question on the slides.
Only one question.
Yeah, can you read it?
So, with proper width and order of consistency to be enforced, the
Hmm.
directional nature of consistencies isn't enough to make it valid.
Yes. So if you remember, when we talked about how much consistency is necessary to be enforced, we had talked about two kinds of widths. One we had said was the min width ordering, uh, but then we saw that if you choose a min width ordering, uh, and as we have seen in today's examples, once we introduce directional consistency, or once we introduce consistency of any form, including directional consistency, we end up inducing new relations. So in this example, for example, a relation between A and D, as you can see on this slide, was introduced. I think it will come on your screen in a moment. Yeah. So you can see here that in the constraint graph on the top, a new relation A and D is introduced. So what is the effect of this adding this new relation between A and D? We have increased the width of this variable D. Originally, the width of this variable was 2, and therefore the width of the graph was 2. But you can see that the induced width of this graph, once we do directional path consistency, has become 3 essentially. So when the width of graph is 3, how much consistency is necessary? So intuitively, you can see that all the three ancestors of D, or all the three parents of D, which are A, B, and C in this case, must be given such values that there is a value for D, and this means 4 consistency. Okay, so why 4 consistency? Because the width of the induced width of the graph is 3, and therefore you need 3 plus 1, which is 4 consistency. So the question is, how do we decide how much consistency to enforce? One way to do that is to first find the induced width of the graph by choosing some good induced width offering and ordering. And remember that while min width ordering can be done in a greedy fashion perfectly, induced width of ordering to get the min induced width ordering is a NP complete problem, and it's not an easy problem to solve. But we can try some heuristics like min fill that we saw in the class, and then once we have an induced width, then we can decide how much consistency to input. The next thing that one talks about is adaptive consistency, and these are the lectures that we are doing currently. And I think next week's assignments are on adaptive consistency. So, what adaptive consistency says is that for each node you must do a different amount of consistency. So, if you look at this constraint graph on the top here, E has only one parent, so you just need to make sure that the domain of D has values which are consistent with E. But D has 3 parents after the induced graph, and therefore you have to ensure 4 consistency, which means that you must be able to give any values to A, B, and C, and you will find a value for D. So for D, you need to do only 4 consistency. For C, you need to do again only R consistency. That's enough. And likewise for B, R consistency is enough. So adaptive consistency goes back from the last to the first, does some amount of consistency enforcement, which may change the width of the graph. But when it goes to the next variable, it will know how much consistency to enforce. And that's something that we are doing in the current set of lectures, and next assignment or the lectures that will come in the next week. I think on this Monday that we see, we look at adaptive consistency.
Thus, checking adds extra complexity to the search.
Yes, that's an interesting question. See, when you are checking whether a pair of variables is consistent or a relation is consistent with respect to another variable, you have to do this extra work essentially. So, which basically means that you have to somehow manage uh, the the representation carefully, and maybe you have to use some kind of hashing to be able to check for which variables are related to which variables, and there is certain amount of optimization which can be done over there. Okay, so if we have no more questions, I'll stop sharing the slides. So I'll stop sharing the slides. To do control A or something. Okay. I need to get to uh, that page too. Yeah. Okay, so here you can see me finally, and thank you for joining for this live broadcast. If you have any more questions, we can continue looking at them in the forum. Okay? So please do come to the forum, and it was nice talking to you. And I'll end the broadcast here. Thank you for being here.